Good evening to one and all. Is the audio clear? And the video also? Thank you. So let us begin our today's session. Before that, any queries on the previous session to anyone? There we have discussed the concept of order of an element. Can you recollect the definition one more time? So can you say what is meant by order of an element? So order is nothing but the least positive integer such that a power n is equal to identity. Can you recollect that? Right. So in today's session, let us discuss some concepts with regard to order of an element. Then we start the subtopic. It is subgroups. So this is the objective of today's session. So first we discuss about some concepts with regard to the order of an element, the results, etc., etc. Then we discuss about the concept of subgroups and problems and theorems related to this. You please take a note of that. By default, whether you take a finite group or infinite group, you are defining the order, that's all. Please understand one thing, that if you take the case of infinite group, every element will possess an order because you are raising the powers of that group. At a particular power, you will get identity. Infinite group means here you are having infinite number of elements in that. That is the main concern. It doesn't mean that every element has order infinite in that. It is totally different issue. You observe the difference. Because you have understood one thing, that whenever you take an element in a group, its order is always less than or equal to group order. So for the finite cases, you can do. For the infinite cases, order will exist. So depending upon your need, you are going to discover what is the order of a particular element. That's it. But this is the standard. Whether you take the finite one or infinite one, order of the element is always less than or equal to order of the group. Yes, order of an element can be infinite because you are going to study one concept, that is cyclic groups. So let me say, if you consider an infinite group where every element is generated by 1. So while multiplying the elements of it, you are going to get all the elements of the group. Since the group contains infinite number of elements, order of this element is also infinite. So we will learn those things separately. I will give the thing that suppose G is infinite. So there is an element in A, in G, that's it. So if you raise the powers of A, all are distinct, such that all these values belongs to G. Since the powers are infinite, G is also infinite. See, if you observe the element A, you cannot find a positive integer n such that A power n is equal to E. This case is not possible here. So what happened? Order of an element is nothing but infinite there. Did you get it now? So there are certain elements where their order is equal to the group order. That's it. The simple example is, if you take Z comma plus, it is an infinite group. here you can observe that 1 generates whole Z because every element is a multiple of 1. See here the operation is plus. So if you add repeatedly 1 and so on, you are going to get Z. So 1 generates the whole set Z. That we can consider. Okay? Right? Now let us take the case of order of an element again. Suppose you take a group G. It has a property that except identity element, every element has order 2. You consider a group G, except identity element, every element has order 2. Then the group what you have taken will become abelian group. Now let us prove this result. Difference between semigroup and subgroup is, I will give the definition. Semigroup means a set with an operation satisfying only two properties, closure and associative. If you talk about subgroup, it is a subset as well as a group. That is why we are calling it as a subgroup. Okay? That is the main difference between these two. Right? Yeah. Suppose you take a group G. Here I have taken a part, say H. It is a subset of the group and it itself is a group. Suppose G has the operation plus, H also has the operation plus. With the same operation, H becomes a group. That is why we are calling it as a subgroup of G. So if you observe the word subgroup, it is a subset as well as a group for the given group. Now is that clear? Fine. Now let us go back. This is actually we want to discuss. I have considered a group in which except identity element, every element has order 2. So G becomes abelian with that property. So how to prove that? Whenever you take two elements G, we have to show that AB is equal to BA. That we have to show. Now, order 2 means if you consider the power 2, it will exhibit identity. So, you can say that A square is equal to E and B square is equal to E. Accepted? As I have taken two elements in the group. Now, from A square equal to E, what we can say? You observe the property and definitions of identity element, inverse of an element. If A square is equal to E, can we say that the inverse of A is nothing but A itself? If A has order 2, from this can we say that inverse of A is nothing but A itself, everyone? Right. Similarly, the inverse of B is nothing but B itself. Now what happens? By closure law, AB whole square is equal to identity. That we can say. Because every element except identity has order 2. Since by closure law, AB is also an element in G, and with the property of G, we can say AB whole square equal to identity. If you have a small doubt, you can write like, by closure law, AB belongs to G, and with the property of G, AB whole square is equal to identity. Therefore, we can say that AB whole inverse is equal to AB. Clear? As we know, elements in a group satisfies law of integral exponents. So on the LHS, you can write that B inverse A inverse is equal to AB, because AB whole inverse is nothing but B inverse A inverse. As we know, B inverse equal to B and A inverse equal to A, we can say that AB is equal to BA. Therefore, G becomes abelian. That was the solution. You please take a note of that. After noting, please inform. Any questions or any doubts you can ask. Right? Now, the other property is, suppose G is a group and order of A is equal to N. If P is prime to N, then order of A power P is also N. You please take a note of it. This is also a good result to discuss with. So, if you observe the given hypothesis, I have considered a group and I took an element A in G whose order is N. So, immediately I can say that A power N is equal to identity. Now, what happens by closure law? If you raise the powers of A square, A cube, A power 4, etc., all these elements belong to G. That is common. So, I have taken a particular power P. So, I have considered the power P to the element A. If the power what you have considered is relatively prime to the order, it is nothing but GCD of P comma N is equal to 1. Then the element A power P also exhibits the same order N that we need to show. Okay? Is it understood? Yes or no? Or you want me to repeat the statement again? Yeah, I will see. So this is the group G, in which I have taken an element A, whose order is n. So I got A power n is equal to E. Clear? Right. Since it is a group, if you apply closure law, A square, A cube, A power 4, etc., these values also belong to G. Agree? So among these elements, I pick up a power P. You can take A power 4, A power 10, A power 100, any power you take. The power has a property that P and N both are relatively prime. GCD of P comma N is equal to 1. So in other words, let me say order of A is equal to 6. I have considered A power 11. Now what happens? 11 and 6 are relatively prime. Agree? So A power 11 also has same order 6. That is what I am discussing. Clear now? Is everyone clear with the task? What it is given actually? Okay. So since we have to show that order of A power P is n, first of all, let us take that order of A power P is m. Let us assume that. Please understand, if n is equal to 5, P is equal to 3, that case generally not possible, even though if you say, as you mention, order of A is equal to n, it means that, see, please understand that here P is equal to 3 means this is the element A. I have taken its order is 5. A square means I multiplied A into A. I got a new element. A cube means A into A into A. I got distinct element, because as we mentioned order of A is equal to 5. It means that A power 1, A power 2, A power 3, A power 4 all are distinct values, and A power 5 is nothing but identity. So if you take, this is A power P. So if you consider the order of A cube separately, that means you are raising the powers of A cube whole power 1, A cube whole square, etc., etc. It also is also order 5. That's the actual thing. Clear? It also has order 5. That means if you consider A cube 5 times, A cube into A cube into A cube into A cube 5 times, then you will get identity. Now is that clear? So you can take the power less than n and more than n, whatever the case may be. Any power you can consider. Right. Now, as per the question problem, our claim is we have to show order of A is equal to order of A power P. It is nothing but you have to show n is equal to m. So whenever two numbers are there, how do we show that they are equal? One is less than the other, or one divides the other. So if you want to show n is equal to m, two numbers are equal, we can prove by the way that m less than or equal to n and n less than or equal to m. By showing this, we can say they are equal. Contradiction is also other case. When general logic is not applicable, then in that case we take contradiction, because we have different approaches. This is the general approach. If you want to show that two sets are equal, generally we say that one set is subset to the other. Therefore, the two sets will become equal. The general thinking. Agree? It is also the same case here. So, first of all, I will consider a power p whole power n, because I have to show order of a power p is equal to n. It means that if I consider the power n for the element a power p, I should get identity in the first place. Otherwise, I cannot decide the order. So this is nothing but a power pn, nothing but a power n whole power p is equal to identity power p equal to identity. Therefore, order of a power p is less than or equal to n, that is m less than or equal to n. Please observe what I have written. If I want to show that an element has order a number, so if you raise the element up to that power, you should get identity. Otherwise, you cannot decide it is an order or not. Because order by default gives identity if you raise the power, isn't it? That's why in the first place, I have raised the element power up to n times so that I got identity. So, since order means the least positive integer, I don't know the connection between order of a power p and the power. So, since order is the least positive integer, I am saying that order of a power p must be less than or equal to n. So, m is less than or equal to n. Okay? Clear? Any doubts for anybody? Fine. Then, there is one more point given in the problem that p is prime to n. So, you have GCD of p comma n is equal to 1. Now, see, whenever two numbers are relatively prime, we can find integers such that there exist integers x comma y such that px plus ny is equal to 1. This property we learned in number theory in school level. Could you recollect? Euclid's division algorithm, real number properties, etc., etc. It is possible to have like this. If you have a doubt, you will give me numbers which are relatively prime, then we can discuss. There exist integers x and y such that px plus ny is equal to 1. You want to check or not necessary? Fine. If you want to check, you give me numbers. What is p, what is n? We will check what is x and what is y. Alright. So, if you consider a power 1, from this notation you can have a power px plus ny. So, a power px into a power ny equals to a power p whole power x into a power n whole power y right. So, if you take 29 and 31, so what are the integers? I can say that px plus ny is equal to 1. So, in that first place, you can say that 29 and 31, you can say You consider the multiples of them so that you will get a difference between them as 1. If you raise the powers of them, so there must be a small gap that the difference is 1. You take one number as positive and one number as negative. That's it. The logic if you want to check. Let me say, since we have taken the case of prime numbers, isn't it? These two are prime numbers you are giving to me, right? Fine. Let me say, let us do with small numbers, say 3 and 5. Now you raise the power, you multiply them, 3 into 1, 3 into 2, 3 into 3, 3 into 4, 3 into 5, 3 into 6, 3 into 7. And for 5, 5 into 1, 5 into 2, 5 into 3, 5 into 4. So this gives 20, this gives 21. So what happened? You can say 3 into 7 plus 5 into minus 4, so that you will get 1. Agree? Similarly, if you take 29 and 31, you keep on multiplying with 1, 2, 3, 4, 5 and so on. For 31 as well as 29, each time you observe the difference, there definitely you will get 1 while raising the powers of them. Because here 3 7s 21, 5 4s 20. So each time as and when you compare, the difference will become 1 at certain level for different powers. That's it. It is possible for every two numbers which are relatively prime. That is also correct. That is also correct. I am saying if you want to think about big numbers, you can think about big numbers. The smallest possible case is 3 into 2, 5 into 1, 5 into minus 1. This is 6, this is 5. The difference will be 1. The thing is, immediately you can ask that, is there such pair exactly once or more than once? So, you can have the possibility that such type of numbers will exist so many, not only exactly one, x and y values. That's why I have taken this example. It is always possible depending upon the numbers, because numbers are infinite, right, in existence. The very example you have taken, that 3 and 5, you got two pairs right now. All you need to do is you should know the tables and numbers, you go on multiplying them. That's it. If you consider of huge numbers, we need computers to calculate. Are they going to become 1 for what type of numbers? Right. So this is all I got. So what is my first step? I raised the power of a power p up to n. So I got identity. So I can say that if I raise the element a power p n times, I can get identity. Since I don't know whether n is the smallest value or not, so I can say that m less than or equal to n. That means order of this value must be less than or equal to n. So in the first place, I got the result. Since they are relatively prime, by using the technique of relatively prime of two numbers, I have taken that a power 1 is equal to a power p whole power x. Now, I got this one. To this value, both sides raise the power up to m. Since using the law of integral exponents, the number theory technique, we can write like this. As we know, I have taken that order of a power p is equal to m. So this is nothing but e whole power x e. So what I got? I have raised the element A power up to n times. So I got identity. Since I don't know whether m is the least value or not, so I can say that order of A is less than or equal to m. Therefore, n less than or equal to m. So from 1 and 2, I can say that m is equal to n. Therefore, order of A is equal to order of A power p. Okay. Is it fine for you? So if you understand the definition of order clearly, then this logic will be very familiar to you. Otherwise, you will get confused. How I am saying that m less than or equal to n and n less than or equal to m. Any questions for anybody? How I am writing these values? So is the definition of order of an element is clear for everyone? Then, did you get any confusion in taking the understanding of the result, which is discussed here? So please take a note of it, then we discuss the other part. Then we start with the part subgroups. So please let me know as and when you note it. Yes, please understand, initially I said that every problem is theoretical and logical. The question is, you are going to apply some previous results while proving the other. So every time you are learning different logics. So after reaching certain level, what happens? Since you got command over all these results and the logics, whenever a new problem is given to you, you are going to prove it on your own. There is no reference at all. The best part of abstract algebra is it is totally a different way. Suddenly you can frame new questions. You can frame new logics. Our thing is, I have a target. So in what way I am doing this? You can apply any kind of logic to prove that. That is the best part of abstract algebra. If you take any other math part, there the formula is fixed, logic is fixed. This is the only way to solve for many of the problems. Here in abstract algebra, for the same theorem, you can have different types of proofs. You can write any one thing, the same marks will be awarded. They're the best part of abstract algebra. So initially, logic seems to be totally different for you. But I can say, if you understand the problem here, all I need to show is these two numbers are equal. So the logic I am using is one is less than the other. Since I am proving this problem based on order of an element, so to get these inequalities, I have to show that order of A power P is less than or equal to order of A. Order of A less than or equal to order of A power P. So nothing but you take this number raised to the other number's power. You take another number raised to the power of the other one. That's it. That is the whole thing you have done in these equations. Nothing else. Isn't it? But if you write it in a formal language on board, it totally seems to be different. What is this m less than or equal to n, px, ny, etc., etc. But the fundamental thing is one simple statement. You are proving two numbers, one is less than or equal to other. That's all. It is not at all a formula, it is simply a simple logic, right? So to that, using the definition of order of an element, you have constructed these things. You didn't go beyond any logic. You just used the concept of P is prime to n. You used the concept of order of an element. Nothing else you have used. Not a result at all. Any previous result you have used. That's it. So once you got deeper understanding with regard to the fundamentals, learning abstract algebra is very easy. The best part is, for every chapter you need revision. For abstract algebra, there is no need to revision. Once you master the statements and fundamentals, you can see any theorem, any result, you can just cross check how to prove, that's all, nothing else. There is no need to practice at all. So I will give one more observation that you take a group, I have taken two elements in it. So both have different order. If the orders are relatively prime, then order of the product is equal to mn. This is the statement of the result. The logic is also very similar. Right now, what we have proved. So in the first step, I prove that if I raise AB to the power mn, I will get identity. Second step, I take that order of AB is equal to P. Then I prove that P less than or equal to mn and mn less than or equal to P. So that P is equal to mn will become. The same logic of the previous problem I will use right here. So I will give the picture. You can cross verify it. So at the free time. So just give me a moment. I will send it to you. Just give me a moment. You can cross verify the result. So please check that. I just sent to you in the group right now. The procedure part. Did you get it? Just check in the group right now. Have you got that? So that you can check after the completion of class. If you have a doubt, I will discuss it separately. Right, because I don't want to discuss the same logic again. That will become a boredom for you. Now we are going to start the new part. That is subgroups. So here, as we discussed it earlier, you take a group G, you take a subset H of G. If H itself is a group with same operation on G, we say that H is a subgroup of G. So we are proving the concept of subgroup with the same operation defined on G, not of anything. So if G has operation star, H also has the same operation star. We are not taking a different operation. So group and subgroup will have the same operation. So subgroup, the very word gives that it is a subset and it is also a group. Now, whenever you consider a group, for every group, there will be two subgroups. One is the set having only one element identity. It satisfies all the properties. So the singleton set is a subgroup of G. Second one is G itself is a subgroup because every set is a subgroup to itself, subset to itself. So as in when you consider a group, always it will have two subgroups, identity and G itself. So these two subgroups, we call them as improper subgroups or trivial subgroups. They usually exist. So if we have a diagram for our understanding, if you take G itself a subgroup, that is one, and the single element set identity is a subgroup of G. Apart from this, if you take any subset which is bigger than this, smaller than G, that is also a subgroup, that we call it as proper subgroup. So if you take any set H which is bigger than this and smaller than this, we call it as a proper subgroup or non-trivial subgroup. So these are the names given fundamentally. So as and when you know that H is a subgroup of G, symbolically we represent it as H less than or equal to G, or you can say H less than G. That is symbolic notation. If H is a subgroup of G, you can write like that. So if H is just a subset, not a group, then we call H with a different name, that H is complex of G. So in other words, generally you talk of that every subset we call with the word complex. So every subset we call with the word complex. So complex will become a group having the properties satisfied: closure, associative, identity, inverse. Okay. So please take a note of these definitions. After noting, please tell. Have you noted? Now, there are certain properties satisfied by subsets, that is, the complexes of a group. Complex of a group means it is a subset of the group. The subset may become a group or not, but generally you can say the technical word of a subset is complex. That's it. The technical word of a subset is complex. That means some authors use the word complex in place of subset. Some authors use the word subset as it is in writing the textbooks. That is why I am giving the word complex. Okay. So complex will become a subgroup if it satisfies the four properties. Are you getting confused with the word complex? I will give simple thing. Subset, complex, both are same. We are calling subset with another name, complex. So subset will become a group. So as complex will become a group. That's it. Fine. Is that making sense? right? I mean, while reading some standard textbooks, some authors use the word subset as it is. Some authors will use the word complex in place of subset. There you will get confusion. What is meant by complex separately? So the non-empty subset, what you are taking in a group, we are calling it with the other name complex. There is a technical word. Just like, let me say, you know this word RAM in computer science? Yes or no? The abbreviation is random access memory. Am I correct? So generally, people call it as RAM, but I am a computer science student, so I call it as random access memory instead of calling it as RAM. But both are same, isn't it? Just like subset, complex, the technical word. You feel that the pronunciation thing is different, but both are same. You can call RAM also with another name, maybe cache memory, etc. There is also other name for it, RAM. Just like that. So, I will say, let me say M is a complex. Nothing but the subset of a group. So, for this set, I am defining a new set. M inverse, such that for every element X inverse will belong here. I will technically write like this. So if you take any element, its inverse will belong to this set. So let me say this is the group G. This is the set M. This is the set M inverse. Now what happens if I take X here? X inverse will be here. If I take Y here, Y inverse will be here. So for every element, corresponding inverse element will belong to this set. Did you understand? So, but actually, this is a subset of the group. This is a subset of the group. That's it. And the common thing is, these will have the common part identity, because inverse of identity is identity itself. Now what happens while checking with the properties of subgroup? If M is a subgroup, then M inverse M both are equal. So these two will become equal sets. They will join together. They will become one. That is the result. So for these results, I will give the proof in Telegram. You can check them. These are not that much important. While reading the proof, you can understand the logic. So after the completion of the class, I will give the proof for them. You can check. I will discuss with the important proofs which are given the exam point of view. Okay, because if you read more number of theorems, you will get scared of this subject. What is this, all these things? So the property is, the set what you have taken is a subgroup, then these two sets will become equal. M is equal to M inverse. If you use the symbol H, if H is a subgroup, then H equal to H inverse. Right? And the converse is not true. That means if the two sets are equal, then M is subgroup. You will get a question. So one part is clear, the other one is not correct. Because you can take a small example. Suppose I have taken the set 1 minus 1, or I can say the sets, I will take the part, I will take the set I comma minus I. This is equal to m, let me say. So what will be m inverse? Again the same thing will come, because for I, minus I is the inverse. For minus I is the inverse. So both are equal. But this is not a subgroup, because for these elements, if you multiply these two, the result is 1, which does not belong to m. So here m inverse both are equal, but m is not a subgroup. So only this part is correct, the converse need not be true. Okay? Is it clear? Right. So the other result is, so how do we multiply subsets? Say I have taken two sets, H and K. So how I am multiplying them? It is nothing but set of all xy such that x belongs to H, y belongs to K. So you take one element from the first set, one element from the second set, you simply multiply them. That's all. So if you want to calculate the inverse of this set, HK whole inverse, it is nothing but K inverse, H inverse. That will come. Right? So it is just like I have given two sets, how you are going to multiply? You fix one element, with this element you multiply all the elements of the other set. Again, you fix second element, with this element you multiply all the elements of the other set, so that you will get this type of thing. This is nothing but multiplication of subsets. The interesting thing here is multiplication of sets is associative. That means if you take three sets A, B, C, in either the you multiply, they will become equal. So they need not satisfy commutative property, they will satisfy associative property. So in the sense, commutative property means AB is equal to BA, sometimes possible, sometimes not possible, but associativity always satisfied. Because if you take A is nothing but set of 2 by 2 matrices, B is also nothing but some set of 2 by 2 matrices. So if you multiply them, AB is equal to BA, can you say I take one matrix here, one matrix here, can always the product is equal? They satisfy the commutative property in matrices? No, sometimes they are equal, sometimes not, maybe may not. Similarly, if you take A is set of functions, B is set of functions, is F circle G is equal to G circle F always? It is also the same case. Sometimes it is correct, sometimes it is not correct. So if you talk of commutative with regard to the multiplication of sets, sometimes it is possible, sometimes not. But always associativity is correct, because if you take functions, F circle, G circle, H, they will satisfy associative property. So if you take the other case, matrices also satisfy the associative property. You agree? That's it. So multiplication of subsets satisfy associativity. Commutativity is depending upon the case. Now there are some interesting observations which we need to know. So one is, if H is a subgroup of G, or simply take remove. H is a subgroup of G if and only if H inverse is a subset of H. Second result, H is a subgroup of G. H equal to H. These are two good results. You please take a note of them. Understand one thing then. Identity element in the group and subgroup is same. So for these results, I will give the proof. You can check out that. So if you're interested, you can read them. Otherwise, you can skip the proofs. They are based on the simple logic, the definition. If you understand how the set is defined, then you can easily understand the proof. If you're interested, I will give the discussion later in the next class. So if you have noted, I want to give another discussion about the subgroups concept. So the next thing is so I have considered a group G and I took a subset H in that. So if I want to check H is a subgroup of G or not, what I have to do? I have to verify the four properties: closure, associative, identity, inverse, whether they are satisfied in H or not. So every time a set is given to me, so I have to verify the four properties. It is a very lengthy procedure. So that mathematicians did something that, apart from verifying four conditions, can I check for one condition which is equivalent to all the four? So they have framed certain results. We call them as necessary and sufficient conditions. So apart from verifying the four properties, if the subset you have taken satisfies exactly one condition, immediately we can say that it is a subgroup. So it is just like a checkout case. If the set satisfies the condition, it becomes subgroup. Otherwise, it is not a subgroup. Okay? Clear? Now I will write down the condition for that. So you take that G is a group and H is a subset of G. So while talking about subset, we always think it is a non-empty subset. Don't think of an empty subset. So H is a subgroup of G if and only if for all A, B belongs to H, A dot B inverse belong to H. You take a note of that. So what this condition says, if you take any two elements in H, A, B, so what you are doing, I take the first element as it is, I take the inverse of the second element, I multiply them, so the result must belong to this set. Because basically A, B, C, every element will belong to the group. So the result A dot B inverse must belong to H. If H satisfies that property, then we say that H is a subgroup. So here the interesting thing is, we are proving each and every result of group theory with regard to the operation dot multiplication, because it is very convenient to understand the notation and do the sums. So you have to generalize the condition. What it means, whatever the operation you consider, you are verifying this property. Let me say, suppose H comma plus you have taken. I have taken two elements, A, B belongs to H. So what is meant by that condition? I took the first element as it is. What is the inverse of B with respect to addition? It is nothing but minus B. So this is element, this is second element inverse. I am applying the operation. It must belong to H. So I have to verify A minus B belongs to H or not. Did you understand? What is meant by A dot B inverse actually? Suppose if you say H comma star is the operation. So I have to prove that A star B inverse belong to H. So I take the first element as it is. I take inverse of the second element. Between these two, I am applying the operation. The result must belong to H. Basically, all these values A, B, B inverse belong to the group. So this result must belong to H. If it satisfies, it will become the subgroup. Clear? So this condition we will use for finite case as well as infinite case. The set may be finite or infinite. Whatever the case may be, we use that condition. The another necessary and sufficient condition is, if you talk of finite group, say G is a finite group, H is subset of G, then H is subgroup of G if and only if for all A comma B belongs to H, A dot B belongs to H. This is very interesting condition. You take a finite group. So obviously, whatever the subset you take in that, it is also finite. So if you want to verify whether the finite subset is a group or not, the simple thing is, if you take any two elements in the subset, it must satisfy closure law. So if the subset satisfies closure law only, it becomes subgroup automatically. So this is true for the finite case. Please understand. Not for the infinite case. It is true for finite case. Okay? That is we are going to discuss. I will give the proof for it also right now, because it is also asked in the previous year papers. We will discuss with the proof. Clear? So let us go with the proof. So what we did, we have taken Z is a finite group. H is subset of G. So H is subgroup of G if and only if AB belongs to H for all A comma B belongs to H. Now let us prove it. It is also one of the previous UPSC questions, around 95 to 2000 it was asked in between. So it contains two parts, right? The first part as well as the back part. So let us go with the main part. So what you are doing? You are moving in this way. So you are taking that H is a subgroup. You are proving that H holds this condition. So you assume that H is a subgroup of G. Immediately you can say that H is a group. Therefore, H satisfies the four properties. Agree? So if you take any two elements, if you take any two values in H, immediately by closure law, you can say that A dot B belongs to H. So the first part proof is very trivial because since it is a group, it satisfies all the properties. So closure law will be satisfied by default. Okay? You please take a note of it. We discuss the converse part now. After noting, let me know. Now, the converse part is you are moving in the other direction. So you are assuming that AB belongs to H for all A comma B belongs to H. Please understand that whatever the elements you take, it satisfies the closure law. The elements may be equal or unequal, distinct or not distinct, whatever the case may be, it satisfies the closure law. So if you want to prove that H is a subgroup, you have to show H satisfies four properties. Among the four, already one property is given in the problem. The closure law is also given in the condition. So H I have taken with the first condition. I already mentioned that whenever closure law satisfies, always associative law gets satisfied. So there is no need to verify associative law. It by default holds. So there are two conditions remained with me, that third and fourth. I have to show that H has identity. I have to show that H has inverse. If I prove these two conditions, then H will become a subgroup. You get it? Tell. So now I am going to prove identity. So if you look at the condition, whatever the elements I take, closure law will be satisfied by H. So first of all, let me take an element A belongs to H. So in place of B also, I am taking the same element. So if you fix one element, the other element you fixed as A square, you can say that A cube belongs to H. Are you getting how I am applying the closure law there? You can take the same elements and distinct elements as you wish. It keep on going. So you can say that A square, A cube, so on, all these values belongs to H. It is possible. Yes or no? So here we need to understand that I have taken a finite group. G is finite. So H is also finite. So you are keeping the powers rising, A square, A cube, so on. as per the given condition, all these values must belong to H. How it is possible? Because while raising the powers, some elements will get repeated. Agree? Otherwise, we cannot say that all these elements will belong to H. Yes or no? So if you keep on raising the powers of A infinitely, A square, A cube, A power 4, A power 5 and so on, if you keep on raising the powers, by closure law condition, all must belong to H. That is mandatory. Since H is finite, you cannot insert infinite values in the finite case if all the elements are distinct. But what happens, since it is a mandatory condition, all these powers will belong to H because some powers will get repeated. That means while raising the powers, same elements will be reproduced. Okay. You are getting the concept or not? So if you have a small doubt, take the case 1 minus 1 I minus I. I have raised the powers of I square, I cube, I power 4, I power 5, I power 6, so on. While raising the powers, elements gets repeated, isn't it? You have observed already. So what happens? You can take any power for I power 100, I power 1 lakh, I power 1000. It will be equal to some other power. Elements will get repeated. So here also the same case comes. So while raising the powers, some powers will get repeated. So let us say that there are two powers equal. Let us assume that there are two powers. A power R will be equal to A power S, where R is greater than S. So implies if you consider A power R into A power minus S, it is identity. So what happened? You have taken that A square, A cube, so on. All these powers will belong to H. So here R minus S is also a power. So it also belongs to H. Since A power R minus S is nothing but identity, we can say that identity belongs to H. Agree? Therefore, I have proved the third property. I have proved the third property. I have to prove one more property, that is inverse condition, that I have to prove. So please take a note of this. I will prove with inverse condition. After noting, let me know. So you have taken two numbers, R and S, such that R greater than S. Implies what we can say, R minus S is greater than 0. Implies R minus S minus 1 is greater than or equal to 1. Is it possible to say? Or you can say R minus S minus 1 is greater than or equal to 0, that we can say. Right. So why I am considering this part? Because if I took A belongs to H, inverse of A means if I multiply A with some other number, I should get identity. So if I take A here, you multiply A with A power R minus S minus 1. So it is nothing but A power R minus S. nothing but identity. So what is the inverse of A here? A power r minus s minus 1. So please understand, H contains all the powers of A by closure law. So here you got A power r minus s. Before that you will get A power r minus s minus 1. All these values belongs to H. So if you say that A is an element in H, its inverse is nothing but A power r minus s minus 1. Therefore, H satisfies the inverse property. Therefore, H has all the 4 properties so that it is a group. You please take a note of that. This is the proof of the part. So whenever you take X, its inverse is X power r minus s minus 1. That's all. This case is true for the finite sets, please understand, not for the infinite. Now, if you allow me, I will give a small picture for you. In Telegram group, I will post right now. Just give me a moment. So in this sense, please understand, here A is not only the element, it is not a generator. Let me say, the thing we need to observe here is, if you take H, H will contain, say, A, B, C, D. So H exactly contains 4 elements, let me say. So what happens, if you fix one element, you keep on raising. All these values belongs to H because H has 4 elements only. So among these values, one element is equal to B, one element is equal to C, one element is equal to D. Did you get it? While raising the powers, they will get repeated. Similarly, if you fix an element B, if you keep on raising, since H is finite, you can consider B square, B cube, B power 4, etc., etc. Those powers are becoming equal to one of these 3, the others. So H, A is generating H means you are saying that there exists exactly one element or 2 elements. The whole set will be generated by H. That is possible. That we can call it as the cyclic nature of the set. So it may be or may not be, whatever the case. Suppose let us take the other thing that you have a possibility that you take H having 10 elements. Let me say A, B, C, D, E, F, G, H, I, J. Now, if I fix A, while raising the powers of A, I am getting these elements. But these are not coming. These are coming by some other thing, say H. While raising the powers of H, these things are coming. So what happens? You cannot say that this is a generator of H or this is a generator of H. You cannot say. Occasionally there will be one element generating the whole set. Here, there is no question of generating. Here what you are saying that if you fix one element, if you keep on raising the powers, since by the finite nature of H, the powers will become equal. So if you identify one power r minus H, it will become identity. The previous power is nothing but the inverse of A. There is the whole situation there. Okay. In a shorter manner, let me say, so if you take the element A, if we keep on raising, let me say A power 10 is equal to identity. Then what happens? A power 9 is the inverse of A in this case. But H may contain 100 elements. That doesn't matter. Okay. So don't misunderstand the concept of generating set here, because we didn't start the concept of cyclic groups. We are just thinking about the subgroups part. Does it suffice for you in getting the idea? So if you keep on raising powers of A power 20, A power 30, A power 100 and so on, the same values will come from A to A power 10. That's all. So remaining values are different. You are getting other elements of H. You cannot fix with the other element. There may be so many elements. Let me say, that's what I'm saying actually. If you take the case, say, this is H, 5 elements, all these nothing but generated by A square, A cube, A power 4, A power 5. That's it. Whatever the rest of the elements, B, C, again D square. You take like that. What wrong is there? That is also correct. Don't straight away decide that all the elements are raising the powers, they are generating the other sets. Don't feel like that. They will generate up to some extent. Definitely, AB belong to H. In such case, what happens? If we calculate AB, that may come as power of this way or this way. That's it. So if you multiply A and B, the result may be a power of A, or it will become C, or it will become D square, something else. By closure law, it should belong to H. That's all. By considering closure law only, we are doing this. So just hold on a moment. I am going to send 2 more pictures for you. So just check the Telegram right now. I sent you 2 more pictures. The results, what I have discussed with you. So if you are interested, you can learn these results. The proofs is already there. You can practice them. Or you can simply leave them aside. But the statement is important. Okay? While doing some other results, we are going to make use of these results. You take a note of them. So at this part, I am going to conclude our today's session. We will meet tomorrow and discuss with more concepts. You can take any standard textbook, anything you can take. All these will have the same results. I have given the list of books, right? You can take any book. Thank you and good night.